Right, we're going to carry on with this because I think I accidentally started muting the other one. So this piece of equipment is a beaker. That's a filter funnel. That is a conical flask, and this is a pipette. That mark there is the graduation mark, and it normally is 25 centimeter cubed or 5 centimeter cubed, whatever you want to put in. So if we name these pieces of apparatus beaker, filter funnel, you've got conical flask, conical flask, and then finally you've got your pipette. Alright. Oh, one thing. There's a piece of paper that goes in there. I'll say just simply called filter paper. Let's just do this so then you get to know this. That's your filter paper. That's your filter funnel. That there is your filter funnel. So when you pour stuff down here, the bits that get left behind are called the residue, and then the liquid is the filtrate. Right, let's crack on. Apparatus P contains dilute hydrochloric acid. That is H, hydrogen and chlorine. Litmus indicator. Right. When you put litmus indicator in there, or litmus paper, or so you've got acid, you've got something which is neutral, and you've got alkali. So litmus paper. Oh, let's use another color. Let's just use that. Litmus paper is red and blue. Universal indicator. Universal indicator. That is red and blue. Now, litmus paper becomes purple, and universal indicator becomes green when it's neutral. Right, then you've got, should we do this? Yeah, okay, let's do it. Methyl orange. That's another indicator, and I remember it as Roy. Red, orange, and yellow. Orange and yellow. There's phenolphthalein, but let's do it anyway. I can't see Pink Panther. That's how I remember it. So I can't see, so it is colorless, and then it turns pink in alkali. Right. We're interested in the color when it's acid, so it's gonna be red. And sodium hydroxide, sorry, in this case is potassium hydroxide. Hydroxide is an OH minus ion, The H plus ion makes something acidic. The hydroxide ion makes something alkali. Alkali acidic. Right. So we're saying its litmus indicator is going to be alkali. So alkali litmus is going to be blue. Right, let's move on. Right, so we've got an experiment set up here. You've got your Bunsen burner. You've got organic liquid. Organic liquids produce vapor, which is flammable. It can explode if you put it near a fire, naked flame, and if you give it oxygen. Right. If you look down here, just leave it there. They've removed the naked flame, the Bunsen burner, and put, we can call it is like a kettle. It's a heating element. Okay, it's like a big kettle, hot plate. Then you've got your organic liquid, but have you noticed they've put a loose fitting cover because you don't want pressure to build up because that might cause it to explode, and it reduces the amount of vapors, so it beats the other method with the naked flame. So right, what they're saying is suggest one reason why, and we've said it up there because organic solutions, where are we? Organic, yeah, okay. Liquids or compounds are flammable. Right, okay. A group of students investigated the reaction between marble chips, calcium carbonate. Right here, that symbol should be like that. Right here, you've got calcium carbonate, which is a solid, hydrochloric acid, aqueous. So remember we said you've got solid, liquid, gas, and aqueous. That just means it's in water. So you end up with calcium chloride, aqueous. Water in its pure form is a liquid, and CO2, carbon dioxide, is a gas. So this comes under the remember the ores, bores, corks, and mash. I'm just going to go over this. So this is metal, that is acid, that is a salt, and that is hydrogen. So now listen carefully. If you've got hydrogen, you are expecting bubbles, or another posh word for it is effervescence. Right. This one is the one we're interested in because we've got a carbonate. That's the carbonate. That's calcium carbonate. Calcium carbonate. They've just called them marble chips. Yep. You've got acid. We're expecting water. carbon dioxide, so there we're expecting what? Bubbles or effervescence. And you've got a salt. That is alkali, acid, base, acid, water, salt, water, salt. Okay. So it's those two. It's the third one we're interested in, really. So what's going to happen? They're going to throw marble chips in here. And how long they're going to check to see how long it took to collect a certain amount of carbon dioxide, by the looks of it, at room temperature. And they're going to change the concentration of the acid. So it makes sense that the more concentrated the acid, the quicker the carbon dioxide is produced. Right. So we want to know two properties. So he's trying to keep the mass the same. So he's keeping the mass the same. What are the two properties? Right, okay. You can say surface area. Right, no, they've used the word amount. That doesn't necessarily mean. So what they're doing is they're counting the number of chips, which is different. So you need to make sure it's not fair having one big. Just say, for example, if you kept 4 marble chips for one experiment and 4 marble chips this size, it won't be fair, because you're going to get more CO2 produced quickly with that. So you have to keep the mass or the moles the same and the surface area the same. If I put that much in one conical flask and the same amount, but I cut them into a fine powder, this would give CO2 quicker because it's got a larger, what's it got? A larger surface area. So you can say mass and the surface area. Let's just stick to surface area. Right, let's keep moving on. Right. The teacher, so these are the 5 students. The teacher said she could only use the results from student 1 because other students had not recorded enough information. Right, so this student used 6 marbles. So the amount, concentration, the amount of gas, and time. So they've done 4 bits of information. Right, the amount, the concentration, the volume, but there's no time. Okay, being a bit lazy there. Right, look, they've not done the amount, they've done the concentration, the volume, and the time, so there's no mass or mass of chips or amount of chips, right? You've used the concentration, you've used the number of chips, and time. So there's no volume. And finally, you've got volume, time, number of chips, but there's no concentration. There's no concentration of the acid used. So that's what was missing. That's why the teacher could only use this one. Right, let's keep going. Okay. The student uses this apparatus to investigate the heat energy released when nitric acid is added to potassium hydroxide. Okay, so you had 25 centimeter cube of potassium hydroxide in a polystyrene cup. That's polystyrene is a plastic which is a good insulator, so it stops energy being wasted to the surroundings. So it'll go to so the thermometer will record an accurate reading of the amount of heat that's lost. You add 5 centimeter cube of nitric acid, stir the mixture, measure the highest temperature, add it further, and you keep doing that. And measure the highest temperature. Okay. And right, okay, name the piece of apparatus that should be used to measure 25 centimeter cubed of potassium hydroxide. So what they're saying is, this here, what would you use to do that? And the best one is, and it's up there as well, in one of the questions further up. Right, you have a graduation mark there. It's called a pipette. There you go, something like that. That's what it'll be. Okay. Pipette. Because it can measure a precise amount. Right. The result is, that's the starting temperature, because there's no acid. You add 5, it goes up, add 5, it goes up, and you keep going up, and it just keeps going up. But now the question is, the result for 20 centimeter cubed is anomalous. For 20 centimeter cubed, right? Where's 20? There. So why is that? So it's gone up 3, 3, 4, 3, right, 6, and 3. Okay. Suggest 2 possible mistakes other than misreading the thermometer. Right, okay. Remember they were stirring, so they might not have stirred the mixture. You could have added less, so that's 1. You could have added less than 5 centimeter cubed of nitric acid. Nitric acid is HNO3. It's good to know that. Hydrochloric acid is what? HCl. And sulfuric acid is H2SO4. Right. Or you might not have not waited long enough for the maximum temperature. Right. So they're asking us to suggest. So it looks like as if they're going up in 3s and 4s. So if we add 3 to that, we can end up on like 34, 35. Just say. So that's gone up. So that one's fine. That one's fine. So if we have that, if we add 4, it would be, no, that's not 2, can't even count. That was 2. So what we can do is add 4, so it'll be 33, 34. So we could say 33, 34. I would say 33 degrees. Right, okay. Right. So now it's a 3 mark. It's really a math question where you're just substituting in. Right, this is where you've got to be careful. This is what causes me confusion. When you jump between physics and chemistry, these symbols change. But it's the same idea. Energy released is mass times specific heat capacity times the change in temperature, delta T. So what's the mass here? Assume the mass is 1 centimeter cubed is 1 gram. Right, 50. So, right, you started at 50, and sorry, 25. You added another 25. So you've added 50 centimeter cubed, and according to this, that is the same as 50 grams. Then we've got, they've given us specific heat capacity is 4.18. They've given us that. And now we need to work out the change in temperature. So the highest temperature was that. The starting temperature was that. So we do 35 take away 16. Right, which gives us a change in temperature of 19. Right, and we just simply put it into there. So it will be 50 times 4.18 times 19, and the answer is 3970 joules. So they've given us that. So that's just simply substitution. But you need to be aware of these, even if they do give you them. It's good because you can access it. You know it's there. Right. We're reacting magnesium with dilute HCl. Okay. So magnesium is going to be a solid ribbon. Hydrochloric acid is going to be aqueous. All the acids that you're going to see will be aqueous. And you end up with magnesium chloride, which is aqueous, and H2 is a gas. So what happened here? What was MgCl? Why wasn't it MgCl? Right, what we do is we go back. We know magnesium is in group 2, so it's going to form a 2+ ion. Chlorine is in group 7, so it'll form a minus. I'm just going to put 1 there. 1 ion. Now, I'm not interested in the plus at the moment. I'm not interested in the minus. All I'm interested in is, are these two numbers the same? So this number and this number, are they the same? They're not. So what you do is you cross over. That 1 goes there, that 2 goes there. No way. Right, that goes over there. So it's going to end up looking like Mg1Cl2, but we do not need to write this 1. Hello, oh, don't say that, please. Yep, we're playing up again. So let's try that out. Choose a rubber. Hello. Nope, it's playing up again. So we don't need that. I'm going to cross that out. So it will be MgCl2. Right, let's move on. So that's what you do. You've got your stop clock, bung, and so on. Right, look at this. They put clean magnesium ribbon on because magnesium, it'll react with oxygen, form a little layer here of magnesium oxide. So we're just trying to get rid of that so it can react with the magnesium metal. Suggest why the student cleans the magnesium ribbon. to remove. Oh, right, so then you can, for the reaction, for the reaction for the reaction to be quicker, let's just leave it like that. Right, so it quickens up the reaction, otherwise it'll give you a false reading. So just why the student needs to put the bung on quickly, right, is to reduce amount of hydrogen that is lost or escapes. So it gives you a better reading. Suggest when the student should start the stopwatch as soon as the bung that's this thing. So you put your ribbon in, put your acid in, and then throw this straight on top. So what happens? What happens is that so then the gas starts going into the gas syringe and you can read it. As soon as the bung is put on, listen, don't use the word putted. That's wrong. No putted. Okay, next one. A student uses a titration to find the concentration of aqueous ammonia. Right, let's have a look. Right, we'll call it quits here. I'll do this on the next video. Actually, do you know, is this a... yeah, this is apparatus and this is like crazy. Not really apparatus, is it? No, we've got to do it. We've got to do it because we don't want to miss these questions. Right, okay, we'll call it quits there.